It's weird, it's inefficient, because most of that stuff is like cosmic rays and random streaks and stuff like that, so they really have to be cleaned up a lot. But, hey. So we're now in the debris field after the terrestrial planets. We're done with terrestrial planets. So again, Sun will get back to terrestrial planets we treated as a group, and then now we're here and here, actually. So it turns out that there are some asteroids there and there, so you should be a little bit worried. And then on Friday, we'll get to the Jovian planetary systems. Okay, so orbits of terrestrial planets, not amazingly interesting. They're what Kepler said. We got to revisit that a little bit for asteroids because their eccentricity are pretty appreciable, and sometimes they get destabilized and go into funny orbits or non-orbits. And then secondly, they have a new property that we really haven't talked too much about. And we'll talk about where this thing came from, or what did or didn't happen to make or not make an asteroid belt. And then a few misconceptions. I blame the second Star Wars movie, and of course how we know all of this. Because we're really quickly reaching the limit of places where we can set foot on or pass probes by. And we'll be done by the end of the week, actually. So a little bit of history is that this is a really, logarithmic units aside, it's a really suggestive-looking graph. So you guys saw this on, I don't know, day one, where 1 AU, 10 AU, 40 AU, and no matter how you look at it, you know, if you make it logarithmic and condense the information, is that the planets seem to have this like gap in their grill right there. And it would be really just pleasing to the eye if there was a planet in between Mars and Jupiter. People have thought for a very long time, since we were able to figure out distances reliably, is that there really should be a planet there. You can make a legitimate physical argument and say, like, maybe the material that condensed into the planets came out of a uniform disk. Well, what happened to all this material? Or you can be motivated by what motivated these guys. Is two guys named Titus and Bodhi said, we've got this law that tells you how to get the next planet's distance from the previous ones, except it predicts this planet in the middle. And it's just like it's like what you'd call a phenomenological law. It's just, it kind of made sense. Wasn't really motivated by anything. So some hopeful math, I guess. But people were looking, and people were looking really, really, really seriously. And do you know exactly, so for one thing, finding a new planet circa 1750, there was really nothing else out there as far as what captivated people's attention. And in 1746, Neptune was predicted and found, so, this is really on people's agenda if they were astronomers. And this one is really suggestive because, based on Kepler's third law, that if this thing's orbiting every 2.5 years and Jupiter's orbiting every 10 years, is that this thing is orbiting every 5 to 7 years or something like that. So that moves pretty fast, and you should totally be able to see it against the background of stars. Should be doing retrograde stuff like Mars is. It isn't like a planet that's stationary masquerading as a star. Should be able to see it. And in fact, you know exactly where to look for it. You should look in the plane of the E-word, ecliptic, where all the planets hang out. So all the planets and the sun apparently hang out in the ecliptic, and you know why, because we're all condensed out of a plane of gas, but you know exactly where you should look at it. I should look in zodiac signs. And the really serious effort that took place to find it occurred at the end of the 18th century, where this German guy, this is a very German thing to do, he conscripted and organized the 12 best astronomers that he knew of into the heaven police, the Himmelpolizei, and assigned each one of them a zodiac sign and said, you look at this as much as you can, and tell me if there's a planet there, and we'll all coordinate their results. This guy, Giuseppe Piazzi, was not one of the heavenly police. He just happened to be looking at pretty stuff, and he's like, hey, that's moving. So 1801, this thing called Ceres, new planet Ceres, was discovered. This is a modern Hubble Space Telescope image of Ceres. You can tell how these people are being influenced, and what Piazzi was trying to do is he found his Ceres observations. He said, boy, this thing's really dim. It's so much dimmer than Jupiter and Mars. Maybe it's just like a fragment of a planet that got blasted or something like that. He actually said that, got struck by a comet and broke apart. In this book that he published, and you can see there is Jupiter with 4 planets, then there's Mars, and there's Ceres in between them. And so quite obviously he's trying to associate himself with like the tradition of Galileo, and he's like, listen, Galileo found his moons, I found my planet. This is Palermo in Sicily where he's doing the observations. It's not that pretty now. But what he really found is what we now in modern terms call the first asteroid. And we've discovered almost, maybe actually more than 750,000 of them at this point. So take that, Ceres. We still do this naming convention where an asteroid has a number in front of the name, especially the low-numbered ones, indicating the order in which they were discovered. It roughly correlates to size, but it doesn't necessarily mean size. So if somebody says 1 Ceres, they mean the first asteroid discovered, whose name is Ceres. Or 4 Vesta would be the 4th asteroid to have been discovered, whose name is Vesta. So 1801. This is why this was so hard. Obviously, lengths not to scale, but sizes to scale. This is the mighty missing planet. What do you notice about Ceres? It's pretty small. In fact, if you sweep up all of the asteroid belt, you can't make a Earth moon out of it. So this thing, we actually don't even call it a planet. And in the same conference in breadth that I don't want to take credit for that, so astronomers used to kick Pluto out of the club, Ceres got undesignated as a planet. And technically what it is a dwarf planet. And there are like three criteria that you need to satisfy to be a planet. And this one doesn't meet one of them. So what it has done is it's big enough to have squished itself into a sphere. So its own self-gravity has made it like spherical. So all the rocks have been crushed and molded into a sphere. And it's just not big enough to have cleared all the debris from its orbit. And it orbits the sun. So we call these dwarf planets. So spherical things, but they're still in like some debris field around it. Yeah. Planetesimal is a historical term that is something that's going to turn into a planet proper. So if you're a planetesimal, somebody's telling you about planetesimals, they're talking about the early history of the solar system or a solar system. And a planetesimal is this undifferentiated ball of warm stuff that's like lurking through this really primordial solar system environment and pulling gas onto it. Well, I mean, specifically in our solar system, planetesimals were like 4.55 billion years ago. Yeah. And they're basically like undifferentiated blobs of stuff which may turn into planets if they survive that terrible, terrible time. So we got like 750,000 of these things, and because they're really small, they're actually a little bit more subject to gravitational perturbations, and they don't, Ceres is pretty lucky, but they usually don't hang out in the ecliptic, and their orbits are not as close to nearly circular as the planets themselves are. So now we actually have to define and talk a little bit about these orbit describing terms. So there's the eccentricity, and that's exactly what we talked about when we talked about Kepler's laws and orbits themselves. Is the more eccentric you are, the more deviation from a circle you have. So you actually stretch a circular orbit out and out and out. You become a more eccentric ellipse. Secondly, and this becomes important with asteroids and Kuiper belt objects, is you can have an inclination. And somebody has to tell you what they're measuring inclination with respect to. But if your orbit is tilted out of some reference plane, it's called inclined. So in this case, this satellite picture, this is actually some communications satellite, is inclined out of the plane of the equator, Earth's equator, or the celestial equator. So usually if nobody says otherwise, what they're talking about is inclination with respect to the ecliptic, because that's just the natural plane to describe things in the solar system. So it turns out that asteroids typically are reasonably eccentric and reasonably inclined. These aren't asteroids. These are some things we'll get to later, but this is the plane of the ecliptic, and we'll do this first. So this is totally face-on, so you're just looking down into the plane of the ecliptic. What can you tell me about the orbit of this Kuiper belt object, actually also a dwarf planet called Eris? It's really, really stretchy. It's not a perfect circle. So it would have a reasonable eccentricity, exactly. And then Pluto is also looking a little bit eccentric. Neptune doesn't look very eccentric. Okay, so now we look edge on in the plane of the ecliptic. And Neptune you couldn't see. Neptune basically has zero inclination. What do you know about Pluto and Eris? Yes, so Eris is very inclined, almost, like 40 degrees inclined. And then Pluto is also pretty inclined, about 20 degrees. So you need a reference plane to talk about this. But this indicates that something's been pushing these things around, or maybe they formed at like a funny time in the history of the universe or solar system or something like that. So it turns out that on average, asteroids are more inclined and more eccentric than any planet, so in general. Okay, so the first group of asteroids are probably what you think about when you think about asteroids, and this is most of them. So these are the main belt asteroids. They lie in between Mars and Jupiter, and although they're more eccentric and inclined typically than a planet is, they're not like wildly eccentric or inclined. And the main asteroid belt has been carved by these interesting Jupiter resonances where, because Kepler's third law tells you that, if you tell me how far away I am from the sun, I'll tell you how fast you're moving around the sun. That if you're here, every 3 times you go around, Jupiter goes around once, and it tugs you, and it tugs you, and it tugs you. And so these resonances with Jupiter just basically like nudge all of the stuff out of that. So these are the so-called Kirkwood gaps. So there's a little bit of structure in the main belt. This is most of them. So like 600,000 of the, 750,000 asteroids at least are in the main belt. The next group is kind of interesting because it's one of the first things that we'll talk about that involves interesting gravity, and also because these things called the Lagrange Points are where we will park spacecraft in the not too distant future to keep them stable and far away from Earth and shielded from the sun, for instance. Is that there's a group of asteroids, so this is the orbit of Jupiter and the orbit of Mars, and there's a group of asteroids that are both leading and lagging Jupiter by 60 degrees. And they're pretty stable, so they hang out there. So why are they there and nowhere else? Why don't I just have this like full band of asteroids around Jupiter? I feel like Jupiter might like gobble them up or something, right? The sun is absolutely pulling them. And the important part is, so is Jupiter, and this is the point at which it's important. So if you imagine the force of gravity on some asteroid right there at the so-called Lagrange point, you've got some force of gravity from the sun, the force of gravity from Jupiter, and they're actually stabilizing these things. They make these little kind of gravity wells called Lagrange points. And they're absolutely at 60 degrees. Every single planet in orbit would have its own set of Lagrange points. There'll be some like space debris in them in general. Yeah. So for these, because they're all basically the same distance away from the sun, is that so gravity is always attractive, but the sun's gravity will always be pulling inwards as they orbit around. The reason they hang out here is because Jupiter is also pulling them a little bit too. And the two things together tend to make this like clump of asteroids collect there. Is that the answer to your question? So the short story is that you have to care about Jupiter's gravity and the sun's gravity. Exactly. Yeah. Yeah, so there's basically like this attendant cloud in front of Jupiter and behind Jupiter constantly at 60 degrees, and the whole thing will spin around once every 10 years. Yeah. Yes. There are 5. Yes. So the other Lagrange points are on this line. So there are Lagrange points in between the planet and the central body, and then there's one on the far side, which is a little bit weird. And this is the one that we would love to park, for instance, the James Webb Space Telescope in, like our version of that, so our L2. So that sunlight is blocked by Earth. It's constantly in eclipse, and it's not being bathed by, the light of a very, very bright, close star. Yeah. No, it's always, yeah, so why 60 degrees is that it's always 60 degrees just because of the geometry of the problem. Yeah, so, yep. So it's, you add these vectors and you stabilize this thing 60 degrees. Yeah, the general discussion involves something called a Roche lobe. I can put up a link or something. Somebody reminds me on the course website. But you see all the Lagrange points. And none of them are like really, really stable, but they're stable enough. And they're pretty useful to have around. So, yeah, and they're also not as stable as something that's far away from a Jupiter resonance in the main belt. So. Ones that are in there now might not be there in, a billion years, and things that are here might in a billion years have somehow been, trapped in there. I don't know, the way that I tend to think about them is like on a really rainy day, sometimes there are these puddles that form in like little depressions in the ground, and in 2 days they're not there. So it's not like truly a lake or anything like that. It's not a really deep well, but it's enough to trap stuff temporarily. So yeah, truly speaking, Lagrange points aren't like really stable as a two-body orbit would be, perfectly stable, but enough to trap stuff like that. So this is an interesting question. So over billions of years, what you get is the slow migration of planets. So things either go in because of gas drag, or they go out because they gain or lose energy. And as Jupiter sweeps out or sweeps in, what it's going to do is it's going to pull these resonances with it, and it's going to kind of scan through and deplete the asteroid belt. Not completely or appreciably so. But when you talk about the amount of mass that's contained in the asteroid belt, you'll see that obviously something was like combing through and removing mass, and lots of it. So yeah, the asteroid belts are, kind of in a gravitationally nasty environment. They've got the Kirkwood gap and the Jupiter resonances pulling them out on this side, and then maybe they get stuck in a Lagrange point, but then maybe Saturn has something to say about how stable those are. Ceres will probably be there in 1 billion, 2 billion years, but I don't know. If you are a massive body in orbit around another massive body, you have Lagrange points. And that's just a feature of how gravity looks. If there's really light debris, they can be trapped in the Lagrange points. So I don't know what's in Earth's that we haven't put there. Maybe there's some like space junk and comet debris or something like that. But just by virtue of the fact that the main asteroid belt is in between Mars and Jupiter, Jupiter's has collected all of this stuff. And there's also some stuff on the ones that they don't show you. So the other ones like L1 and L2. And L3. That's the weird one. Good. Other questions? Okay. This is the group that everybody tends to focus on. And just to put it in perspective, this is not a large, most of them are main belt asteroids. There are things called Earth crossers. They're not treacherous and out to kill Earth. To be an Earth-crossing asteroid, all it means is that your aphelion is greater than 1 AU, so the farthest you are away from the sun is greater than 1 astronomical unit, and the closest that you're ever going to be to the sun is closer than 1 AU. So it looks terrifying, right? So we're Earth, and there are all these things like Quetzalcoatl is going to zap us or something like that. What's not depicted on this picture, much as it wasn't for the moon phases exercise, that makes it not as scary as you might think. Yeah, exactly. And now we know the term for it is inclination, is that all these things are probably inclined. And so they're probably not actually intersecting Earth's orbit. There's a subclass of Earth-crossing asteroids called potentially hazardous asteroids. That's exactly what you think it means. They're potentially hazardous asteroids. And because we know Newton's laws so well, we're keeping track of them to a pretty high degree of certainty. these things, they're an important group because we care about them. They were destabilized by Jupiter or by other processes. Maybe they got hit by some other asteroid and destabilized. The good news is we're keeping pretty good track of them. So those three groups, I think, are the important ones. There are actually many more. There are things like centaurs and things like that. You can really nerd out on asteroids, but the three groups, I think it would be, you know more than 99.99999% of people on Earth about asteroids. If you know about main belt with Kirkwood gaps, why the Kirkwood gaps exist, Trojans, why they're there, and then, of course, the Earth crossers. Everybody probably knows that happens. Okay, so any questions about orbits? So the remaining questions are how much stuff is in the stuff and composition. So what are asteroids made out of? So this is a textbook picture, and it's artistic, and it's terrible. This is not what our asteroid belt looks like at all. I think somebody asked this, and I'm sorry to pollute your head with like model and analogy after model and analogy. But if you want like a genuine depiction of how much material is in the asteroid belt, like imagine I gave you all a grain of salt. Everybody has their own personal grain of salt in their hand. And we all had to spread out like one person per city block. So like 2 people in Cal Anderson, and then 1 person, I'll stay here, and then you guys have to walk around all of Seattle. Is that this is not like, this is not Empire Strikes Back successfully, not, and the odds of successfully navigating our asteroid belt are pretty high. We just shot Voyager through it, no problem. So this is wrong, and if you swept up all of the asteroids that we know of, like all the appreciable size, we've seen them, we're tracking them asteroids, all 750,000 of them, get like 5% of the moon's mass, which has something to do with the material they're made out of, but it's also 5% of the moon's mass. So there's actually something interesting in the story, is that this missing planet, if you go all the way back here, is not a missing planet. It isn't a destroyed planet. It's something else. So why all the material that should have been here got so wildly depleted is still kind of an open question. So that having been said, is there are 750,000 of them, and they do interact, So the odds of getting bitten by a shark when you go swimming is very low, but still it happens to like 3 people a year because there are just so many people swimming. So there are asteroid-asteroid interactions. This is an asteroid called Ida, and Ida has captured a moon called Dactyl, and Dactyl is happily orbiting Ida. And had they been a little bit situated differently, Ida may have thrown Dactyl off in some random direction and had it come whiz by Earth or something like that. So they do interact. You have 750,000 squared potential interactions. So the other misconception, sometimes people just say like, well, yeah, the gravity of Jupiter just kept a planet from truly forming. And if that were true, you wouldn't see what you do see. So if we talk about the composition of these things. So 4 Vesta, 4th asteroid discovered. It's nice. You see this weird sort of crust on it. It's got like it looks like somebody took a piece of magma, so a piece of basalt, and just threw it out into space. And what cooked the basalt was radioactive aluminum from really early in the history of the solar system. So it's got this like cooked crust of silicates that look like they're from our mantle. And then 216 Cleopatra, this is a radio image of it spinning as it tumbles through space. It's this like weird sort of dog bone of metal. So it's got to be metal if it's maintaining that shape and spinning. If it were just aggregate of rubble, it would fly apart. Eros is really fluffy ice and rock. If you imagine that you loosely packed a snowball or something like that, that's basically Eros. You hit it with a hammer, the thing might create a garbage can sized crater. So it's really, really fluffy and icy. This means that something happened, right? So there needed to be some sort of differentiation, because otherwise what I'm saying is in this kind of primitive sea out of which the asteroid belt started condensing, is that somehow the metal only hung out with the metal and the silicates only hung out with the silicates, and all the carbons and ices found each other like some weird chemical middle school dance. is that they needed to have been a bigger body to differentiate the metal to the center through gravity, and the silicates to the outside, and then the carbons and ices either outside still or just not participating. These are the types and groups into which you tend to classify asteroids. And it's exactly what you think. M is for metal, so they're M types. It's about 8% of the whole thing. S is for silicon, like magma and like obsidian, glassy rocks, things like that. Stuff from the mantle-ish. About 20% is S-type, S for silicon, and then the rest mostly are C-type, which are ices and carbon. And they're really, really, really dark, and they're really, really fluffy, and they're really, really, really undifferentiated. So Piazzi's conjecture that there was a fully formed planet that got hit by something tremendous also cannot possibly be right, because this would be the weirdest planet that anybody has ever seen. So these are our terrestrial planets with composition for comparison. What sort of planet is 8% core, 17% mantle, and 75% crust? So really what went on with the asteroid belt is that nobody really knows. There must have been some differentiation. There must have been some sort of primitive bodies growing, maybe planetesimals. There must have been some violent events. But like the simple story that, Jupiter kept something from forming can't possibly be right. There has to be something more going on. And in particular, that 5% of the moon's mass, there should be much more stuff there. So something either depleted the asteroid belt or, there are things in there that got beaten up. So it actually is an ongoing story, absolutely. Okay. So any questions about the classification? If you find one, they'll name it after you. So how do we know all this stuff? This is towards the end of when we can do this. We actually have missions that go out and take stuff off of asteroids and either examine them there, or one mission is actually thinking about returning stuff. Telescopic observations, this is the first time we'll talk about spectroscopy. They send stuff to us. Then I'll mention this thing called occultations really quickly. So we have gone by asteroids, taken pictures, and actually gone in and tried to grab some stuff off of them. This idea of spectroscopy is something that we'll basically spend the second half of the course doing, because we're out of stuff that we can go and, look at, take samples from. Then I'll just start the discussion of spectroscopy by saying this, is what are all these things? No, they're not. So that one's a neon sign, and that's a neon sign. That's a helium sign. That's a hydrogen sign. That's a krypton sign. Yeah. How do I know that? Exactly. So everything that you see on the periodic table of elements, if you zap it with electricity and you jiggle their electrons around, they emit a specific type of color, which is awesome, because everything that's emitting light is basically broadcasting, this is what I'm made of. And this is the idea of spectroscopy. So everything has a unique fingerprint, and now you can hassle people about neon signs. Be a jerk. Let's do a neon sign. I'll just throw this out there because it's kind of neat, and some very awesome amateur science beats the Hubble Space Telescope. So this is Hubble Space Telescope's best image of Ceres. One Ceres, the biggest one of all of them. And a group of people, I think the first one that people observed was in 58 or something like that. People have been looking for a while. There's this idea, actually, based on something like this. So what is this that you're looking at here? Yeah. Specifically, it's the shadow of the moon from the sun. So this is a solar eclipse, if I were standing there, total solar eclipse. And that's the shadow that the moon casts from the sun. And somebody's like, well, that's pretty neat. Yeah. Is what? Yeah, so that would be the umbra, and then the penumbra would be the thinner circle around that. Yeah, you can actually see it pretty well in the reflection of the clouds. That's the umbral shadow. Mm-hmm. Yeah. So somebody said, well, if we can see the shadow of the moon is cast by the sun, that's a rocky body in a star. Why can't we see the shadow cast by an asteroid from an arbitrary star? So lots of asteroids and lots of stars. Which, when you phrase it like that, it sounds like a pretty idiotic thing to try to look for. What you're really looking for is an asteroid passing in front of a star. And that's probably pretty likely because we have lots of stars and lots of asteroids. So if you're looking at a star and it winks out because an asteroid has gone over it and then it winks back into existence, you're like, great, I actually know Kepler's third law. I know how fast the asteroid is going, so I can figure out how big it is. And that's actually a pretty precise thing to do. And if I want to go crazy with this, if I put all my friends across this and they all observe this shadow of the moon passing over, this one would see a briefer time, longer time, longer time, longer time, longer time. We could make a picture of the moon based on these timings. So this is a picture of an asteroid, 100 kilometer across asteroid, based on all these people looking at a star, timing when it winks out, timing when it winks back. And this is, maybe like 10% of the size of Ceres, and you can actually see structure on it. So this process, and lots of amateur astronomers do this, actually, like kind of one of the really good scientific things amateurs can do these days, is the idea of asteroidal occultations gets so much better data, and you can predict them really well. We're really good at predicting stuff. It's just kind of neat. Finally, we know about them because every once in a while we get unrequested sample return missions from the asteroid belt. Some guy playing Xbox in Chicago in like 2003, and then a meteorite just crashed through his roof. It happens. Worth a lot of money, I guess, if you survive. And what they tell is the exact same story. Is they're primitive meteorites, which totally look like just undifferentiated basic rock, and then there are ones that seem to have been heat processed. So there maybe was a rocky differentiated body. The best place to go to look for meteorites if you don't want to wait until one crashes into your home is Antarctica. Actually, guesses about why? Fewer burn up. That's a reasonable thought. It's neat because it's got nothing to do with astronomy whatsoever. Nope. If I see a rock in Antarctica, it probably came from above, right? So Antarctica has this wonderful feature. One, it's like really, really, really bright because it's totally covered in snow. And secondly, all the rocks are under the snow. So if you see something on top of the snow, one, it stands out and contrasts really well. And secondly, it's almost certainly came from above. So just for the the contrast purposes, Antarctica and the Arctic Circle are great places to look for this. Yeah, I think the back when people in Europe thought that it was inconceivable that rocks would fall down from the heavens because they were perfect and incorruptible, I think like Inuit people were just searching these things out because they're really, really hard, durable stone. Called them star shit. Okay, so the destabilized orbits, if little things show up, you can sell it to the Smithsonian. If big things show up, there might be some issues. Again, we talked about this. Destabilized orbits are badness. This is a so-called Barringer crater in Arizona. It's about a mile across. That's from an impactor about 50,000 years ago. That's pretty recent history geologically. This is the Tunguska crater from 1908, an impact of probably a comet. Also giant crater. It's kind of hard to tell because it wasn't in a really preservative environment. And then more or less like, most of the Caribbean, and it's hard to tell really, but there's like rings of sinkholes and cenotes and the limestone around it from the shock waves. But most of this feature is from 65 million years ago when we got hit by something about probably about 10 kilometers across. And why don't we notice this on a day-to-day basis, actually? Yeah, lots burn up. The ones that do hit us, 2/3 of the time, what are they going to hit? Water. And we also overestimate, you tend to think about like Seattle and the Pacific Northwest, for instance, because we live here. Most of the landmass on planet Earth is uninhabited and inhospitable. For instance, like Siberia and Saharan Africa and stuff like that. So this Hollywood conception where, the asteroid comes and they've got like wonderful aim, and one hits the Eiffel Tower and another one like hits Mount Rushmore, and it's so preposterous. Like mostly they hit the water, but they hit a lot. Yeah, sorry, just can't not do it. And if you want to know how frequently, so Tunguska actually is something about that big enough to like shake the Earth and have everybody go, oh my gosh, that happens once every 100 years or so. The one that was also in Siberia a few years ago, did you guys see that? Like the fireball over Chelyabinsk? Yeah, absolutely. That's like yearly at least. So one of those hits every year or so. It's just that happened to be over a place where a lot of people had cell phone cameras and there were people. Yeah. I always wonder why like dash cams are so common in Russia. I think it's like the cop kleptocracy or something. You protect yourself. But so this is where we start caring, is that if the asteroid is about 1 kilometer across and bigger, then we start having like global consequences. So that happens once every million years or so. So every million years, based on things like looking at the lunar cratering record as a proxy and doing calculations. Every million years, Earth gets smacked by something, and this thing, once every 100 million years, for instance, is the thing that the geologist has called the KT impact, which of course is what? One more time. Sorry. So this is asteroid stuff. Again, I'm happy to answer any questions, but the real basic thing I think you guys should know is the 3 really big parts of asteroids by orbit: main belt Trojans, Earth crossers, and then a little bit about their composition, which is to say it's not uniform, and it kind of gives you the sense that something was there and started trying to differentiate. Any questions about that? You guys want a quiz? Okay. Yeah, computers, cell phones away. When you look like you're ready for a quiz, I will give you a quiz.